Hello, welcome to Mystery Science. Today we're going to be looking at the Edexcel CP2a Resultant Forces, part of the combined science suite of the Edexcel GCSE. We're going to be looking at representing forces on diagrams using arrows, representing magnitudes and directions. We're going to be able to define what a resultant force is. We're going to be able to calculate what the resultant forces are, and we're going to explain whether forces on objects are balanced or unbalanced. In the next lesson, we're going to talk about why that matters. What I'd like you to do is pause the video or just spend a couple of minutes having a quick look at this do now. This goes back to CP1 if you've been doing the course sequentially. What is the difference between a scalar and a vector property? Give me 3 examples of each. And while you're doing that, I'm going to plug my t-shirt. This is one from my Amazon store, Mr. ET's. It has the neurodiversity loop on it, and it also has the LGBTQ plus pride flag. I have a bunch of these designs on Redbubble. If you want stickers, mugs, travel mugs, all of that kind of stuff, check out my Redbubble shop. If you want this t-shirt and you want it pretty quickly, you get the Amazon quality and Amazon delivery by clicking on the Amazon link below. Right now, after that quick plug, let's have a look at our do now questions. What is the difference between a scalar and a vector property? Well, a scalar property has a magnitude, so it's just a size. For example, speed. I'm going 100 miles an hour. I could be going 100 miles an hour that way, that way, that way, that way. And that was all really confusing because my screen is backwards to where I'm actually pointing. But that's a scalar quantity. It has just a direction. Other examples of scalar quantity you could have include mass. Your mass is your mass. Doesn't matter what direction it's in. And an example of a vector quantity would be velocity. Velocity is like speed, but in a specific direction. And you could have weight. Weight is like mass, but it's in a specific direction, and it's actually a force. So it has a direction and a magnitude. Another scalar property would be distance. 20 meters is 20 meters, but 20 meters could be in a circle. The vector equivalent of that is displacement, which is actually how far you've moved from the origin. So if I start here and I move 10 meters this way, my distance and my displacement are 10 meters. However, if I go 10 meters round in a circle, I've come back to where I've started from, so my displacement is 0. My distance that I've moved is still 10 meters, but actually, where have I really gone? I've gone from here to here. I haven't gone anywhere. So the distance I've traveled, 10 meters, the actual displacement is 0. Okay, so that's a quick recap on vectors and scalars. A vector quantity is one that has both magnitude and direction, whereas scalars only have the magnitude, which is its size. So forces are vector quantities because we need to know the direction they're traveling in, or what direction the force is acting on, as well as how big it is. If I have a force of 20 newtons heading towards my face, I'm a little bit more worried than if I have 20 newtons traveling away from my face. I don't want something that's traveling at my face to carry on traveling, whereas something traveling away from my face I'm all right with, as long as it's not heading towards my Nintendo Switch or my PlayStation. Okay, so here is a question for you. An Olympic cyclist is going round a bend at a mind-bogglingly 19 meters per second. I've looked it up. This is the actual speed they do. You're in my class, and that's twice the length of my lab every second. Now, if I've taught you speed at any point, you know that I always measure the size of my lab, and I measure out 10.64 meters, which in my current lab is just outside the door. And I will walk from the front of my lab to just outside my door, and I will tell you Usain Bolt ran that every second, his average speed, 10.64 meters every second, which is mind-boggling. These Olympic cyclists are going almost twice that speed. So, if they're going around a bend though, let's think about scalars and vectors for a moment. Is their speed changing? Or is their velocity changing? So, let's have a look at this. If you're going at 19 meters per second, you're traveling at 19 meters per second. That is your speed. So if the Olympic tracks are designed so that literally you can almost go at a straight line speed, that's why they're banked, so that you can just keep going. So at 19 meters per second, which is incredibly fast, their speed isn't changing. They're just going round the bend at 19 meters per second. That's a constant speed. But what about their velocity? Velocity is a vector quantity, and that requires a direction and a speed. So if you are going straight at 19 meters per second, your velocity is not changing. However, if you start curving round a bend, your direction changes. If you have a change in direction, you have a change in velocity. So even though their speed is staying the same, their velocity is changing. So as you go around a bend, even if you go around at constant speed, your velocity is constantly changing. If your velocity is changing, technically you're accelerating. And we'll talk more about that later on in this part of the course. All right, let's name some forces. Easy peasy. I've got them right here for you. All you've got to do then is unscramble the letters, work out those anagrams. Pause the video, take a few minutes, do as many as you can. Right, welcome back. So, Gewicht is actually weight. Weight is a force. We've just discussed this. Filt. Anyone? Lift. Guard. Drag. Stirth. Thrust. Suff. Push. Tincreoff. Friction. Stirp. Might be a tricky one. Up thrust. And then finally, Ria Edexcel is air resistance, which you can't see the end of because I'm in the way, but ends CE if you need to help spelling that. All right, so the next few images are going to be of things that have forces acting on them. For example, this is a car, and you can tell it's in motion because the background's all blurry and stuff. What I would like you to do is draw a very quick diagram. Don't draw an accurate car, that'll take you forever. Draw a very quick diagram of a car and then give me the forces, so label the forces where you can. So in this example, we would have an upwards force from the road. We'd have friction and air resistance acting against the car. We have weight pulling the car down. And we have a forwards force from the engine driving the car forwards. Okay, so over the next few images, do a little sketch, and I do mean a sketch, and label those forces if you can. So here's an aeroplane. Pause the video, sketch your aeroplane, label the forces. Welcome back. So our aeroplane, we have some lift from the wings. We have some drag, which is air resistance. We have weight trying to pull the plane back to the earth, and we have thrust from the engines, keeping it moving forward. Here is an Olympic gymnast on the rings. Again, label the diagram. So we have now upwards force from the rings and the gymnast's weight pulling him back down towards the earth. And finally, this diver. Okay, we have up thrust. The water is trying to push him back up to the surface. The weight of the diver is trying to pull him down towards the center of the earth. He has forward force from his flippers as he's flipping along. And there's water resistance or drag trying to slow him down. All right, so in those diagrams, we had the picture of the object and then we had arrows representing the forces. And this is how we represent forces on paper. So this very fine rocket is heading up towards the outer atmosphere. So we'll represent the forces on this rocket by drawing arrows. The length of the arrow represents the size of the force, so the length of the arrow is important. So this rocket has a very large thrust going up into the air and has a weight acting downwards. But if you can have a look at those arrows, the weight is not as large as the thrust, which means there is an overall force, a resultant force. And this is due to the fact that the thrust is larger than the weight. So we have a resultant force going upwards, and we represent that with a third arrow. Now this arrow should be the combined length of the thrust minus the length of the arrow representing the weight. This allows us to calculate forces. If you have a proper scale diagram with a ruler, you can measure the length of each arrow, and if you know what each arrow represents, you can calculate the forces from your final arrow. And we use this in what we call the parallelogram method. And when you did vectors and scalars, you'd have done exactly that. And so forces are just vector addition to find out which the resultant force is. When you've got a rocket going up, you want a resultant force going in the upwards direction, so it gets faster and faster. Or at least you want the forces to balance. And if they're balanced, as I'm going to tell you in the next lesson, the speed of the rocket won't change, but it will at least be going in the right direction. What you don't want is the weight being larger than the thrust. As soon as that happens, then you have a resultant force pointing downwards, and that's very bad for everyone involved, because unfortunately that means your rocket's going to slow down, and then unfortunately if it gets to the wrong speed, it's going to start falling, and you're never going to get that rocket into space, and hopefully you're going to land the rocket and not have it explode on impact. And so you can calculate the resultant force. If your forces are all going in the same direction, you can just add them together. If they're going in the opposite directions, you subtract the smaller one from the bigger one. So in our previous example, the thrust was larger than the weight. You subtract the weight from the thrust, you would end up with the resultant force of the rocket. Let's look at an example. So if I have a cyclist riding along a flat cycle path and he's not pedaling, the air resistance acting upon them is 10 newtons. The friction on the wheels is 5 newtons. What is the resultant force on the bike? Pause the video, see if you can work it out. Okay, welcome back. So if we have our little cyclist here, we're told we have a friction force of 5 newtons and an air resistance of 10 newtons. What is the resultant force? Well, because they're acting in the same direction, we simply add them together. 10 plus 5 gives you 15. They're both in the same direction, so we have a resultant force of 15 newtons in the opposite direction to the cyclist. This means this cyclist is going to be slowing down. You know this, if you're cycling along and you stop pedaling, if you're going on a flat path, then what will happen eventually is you will slow down over a period of time, and eventually you'll fall off your bike. However, if you are pedaling with a force of 25 newtons, that means you have a force going in the positive direction you are traveling. So you have your cyclist, you've still got your 5 Newton force, and you also have the 10 Newton air resistance. So now you add a 25 Newton forward thrust. So now to work out the resultant force, we take our 25 newtons and we take away our drag forces. So again, we can still add these together. That gives us 15 newtons. 25 minus 15 gives you a resultant force of 10 newtons in the direction with which you're traveling. You're going to be speeding up. So these forces, all of these forces here, are what are called unbalanced. And we're going to look at unbalanced forces in the next video, but you can say these are unbalanced because the forces don't add up to 0. If the resultant force is 0, the object has to be either stationary or it's moving at a constant speed. And we say that the forces are balanced. So anytime you look at resultant forces, if you've got 0, then the forces are balanced. Now, we're going to discuss later that that doesn't necessarily mean the object is stationary. It could also be moving. It's just not speeding up or slowing down. All right, so in your book, what I'd like you to do now is draw 2 diagrams of the same object, one with balanced forces and the other with unbalanced forces. Can be as simple or as complex as you like. So here's an example of a balanced force. This coffee cup is, let's say, sat on a table and has a force of 10 newtons pushing up from the table, 10 newtons from its weight, pulling it back down to earth. And this one is unbalanced. We have 10 newtons being pushed up on the coffee cup, but unfortunately 15 newtons going down. This is unbalanced, and this coffee cup is going to be spilling its coffee all over the place. All right, so here again, I would like you to pause the video and calculate the resultant force on these objects. Remember, you don't have to particularly draw really good pictures. I'm interested in you resolving these forces. So have a go, and we're going to go through the answers in a moment for you to mark with your green pens. Right, so here are the answers. Question 1, we had a resultant force of 4 newtons upwards. Question 2, 3.5 newtons downwards. Question 3, 70 newtons upwards. Question 4, 31 newtons to the right. And question 5, 23 newtons to the left. And if you did the extension, then you should have got 5 newtons going down in that diagonal direction. Alright, so in this lesson we have used arrows to represent forces, different sized arrows for different sized forces. We've seen that the resultant force comes when you have a larger force in one direction than you have in the opposite direction. We've been able to calculate these resultant forces, and in the next lesson we're going to talk more about balanced and unbalanced forces and what that resultant force actually means for your object. To wrap up this one though, what I'd like you to do is write down 5 questions to test someone's knowledge. I want you to pretend that you are their teacher, and I want you to really quiz them, get them really thinking on these learning outcomes, please. All right, that's it for this lesson. Stay safe. I'll see you soon.